Magnetization in ferromagnets. Precesses around effective magnetic fields on picosecond timescales, yet standard equations break down when memory effects emerge. We measure entropy production to distinguish true Markovian relaxation from non-Markovian dynamics with information backflow. When inertial effects enter, rotation coupled to angular momentum, the magnetization exhibits additional nutation oscillations. These secondary oscillations create history dependence because the system cannot instantly reach thermal equilibrium. Memory of past trajectories influences present dynamics. Extended equations, including open system coupling to structured baths, generate even richer oscillations. The memory kernel, encoding bath correlation functions, becomes the mechanism through which past states influence present evolution. We compute entropy production rates to quantify this non-Markovian character. Entropy production quantifies irreversibility. Positive rates mean information flows one way to heat. Negative rates mean memory effects drive information back into the system. We measure this rate from probability distributions evolving in spin space. Non-Markovian dynamics show temporary entropy decrease. The Fokker-Planck equation governs probability evolution in spin space. For standard damping alone, we prove the relative entropy, distinguishability from equilibrium, always decreases. Contractivity holds. This mathematical property guarantees positive entropy production rates in standard LLG dynamics. Inertial and open system equations introduce second-order or memory terms. When marginal probability densities are reduced by integrating over unobserved degrees of freedom, contractivity breaks. The reduced evolution becomes non-local in time, creating temporary Negat entropy production rates. Numerically, we simulate 50,000 trajectories of magnetization evolution under each equation. At each time step, we count how many trajectories occupy each region of spin space, building a histogram. From this empirical distribution, we calculate entropy directly using the discretized probability. For the standard LLG equation, entropy production remains strictly positive at all times. We observe monotonic distribution contraction toward equilibrium. The relative entropy curve decreases smoothly without reversals, confirming purely Markovian behavior with no memory effects. With inertial coupling, the entropy production rate becomes negative during brief windows when initial torques are strong. The canted field configuration at 45 degrees to initial magnetization excites nutation most efficiently. Memory effects from angular momentum lag enable temporary backflow of dissipated energy. The open system LLG equation, including structured bath coupling, shows the largest entropy production rate magnitude and most pronounced temporary negativity. Coherent coupling through the memory kernel, the integral convolution of past magnetization with bath response, dominates the dynamics on sub-picosecond scales. The experimental verification requires ultra-fast pump probe spectroscopy on thin ferromagnetic films. Cobalt samples exhibit the predicted multi-oscillation signatures at terahertz frequencies. Hot electron bolometer detection can directly measure entropy production through energy flow measurements, revealing non-Markovian signatures in real materials. Across a wide parameter space, different field orientations, coupling strengths, material parameters, the theoretical predictions remain consistent. Non-Markovianity emerges universally when system timescales match bath correlation timescales. The breakdown of simple damping models occurs around tau 100 femtoseconds. The physical mechanism is straightforward. Inertia and bath memory introduce timescale separation between fast oscillations and slow decay. When these timescales intertwine, oscillations can drive temporary energy return from heat bath to magnetization. This violates Boltzmann's one-way time arrow locally, though total entropy still increases. Understanding non-Markovian magnetization dynamics opens pathways to control ultra-fast spin systems. Engineered baths can suppress unwanted decoherence. Memory effects enable new protocols for information storage and retrieval, and entropy production measurements become diagnostic tools. The boundary between Markovian and non-Markovian evolution is no longer theoretical abstraction, but experimentally measurable signature.